Hello there, ATS EVS 105 students. Dr. Shragi here, and I am here today to finish up our module about climate modeling. We're going to be talking about what models can do for us and so on in a later module, but right now we're just understanding how modeling works. And today we're going to be talking about scenarios. Remember, when we want to create an ensemble of numerical models for understanding the future climates, we're going to want all of these models to have slightly different boundary conditions. In the last lecture, we learned about how we would want the forecasts of weather to have different initial conditions, but if we're going to be understanding, what are the range of outcomes that we can have with regard to climate modeling, we're going to need to have different boundary conditions. And in this context, the important boundary conditions are going to be things like greenhouse gas concentration in the Earth's atmosphere. So what's going to end up actually determining the amount of carbon dioxide in the Earth's atmosphere? Well, if we just take some verbiage from the IPCC report, it says future greenhouse gas emissions are the product of a very vast, dynamic, complex systems determined by driving forces like demographic development, socioeconomic development, and technological change. What are we talking about here when we say demographic development? What we're talking about is changes in population. Clearly, the total population of the Earth has an impact on how much greenhouse gases are emitted into the Earth's atmosphere. Socioeconomic development, what we're really saying there is how rich we are as a society. Are we, if a large part of the Earth's population doesn't have cars, well, those people are not emitting a lot of greenhouse gases, or not producing a lot of greenhouse gases, whereas if all of a sudden everybody's driving a Buick, we have a bigger problem. And also technological change. This is about things like alternatives. If we could develop cost-effective electrical cars, maybe we could change our greenhouse gas emission profile. Or if we could make, make solar power more cost-effective or something like that. Hey, that all sounds like stuff that's outside the natural sciences, and it is. This is going to come to us, the kind of factors that are going to determine how much carbon dioxide gets emitted into the Earth's atmosphere comes to us from things like sociology, economics, engineering, policy, development, and so on. These are all very complicated ideas that are outside the realm of the natural sciences like physics and chemistry and atmospheric science and the climate sciences and so on. This is a very interdisciplinary aspect of what we're doing in this class. More importantly, all this stuff is really, really uncertain. It's very hard to have a sense as to how many gigatons of carbon are we going to be emitting into the Earth's atmosphere, say 70 years from now. But that's an answer we need, or at least we need to have some sense as to how big the range is and so on. Frankly, getting this stuff to work makes modeling the climate itself look pretty easy. And so, to try to figure out how much carbon we might be emitting into the Earth's atmosphere at different times over the rest of the 21st century, we create these scenarios. Scenarios are alternative images as to how the future might unfold, and this is a quote from the IPCC report, and are an appropriate tool with which to analyze how driving forces may influence future emission outcomes and to assess the associated uncertainties. These scenarios can be used to define the boundary conditions in numerical models. I don't want you to have the idea that these are guesses. Okay, I mean, they're guesses, I suppose, in a very glib sense of the word, but entire interdisciplinary teams of scientists get together and start figuring out what would happen if, how much fossil fuel could we actually no longer burn if we were able to deploy more solar panels, if we were able to increase the wind. How long would it take us to have enough wind power generation capacity that we could start taking some coal-fired power plants offline, etc.? I mean, they actually find out things like how long would that take, or how much money would that take, or what's a realistic amount of solar or nuclear or whatever to bring online. And so these scenarios are based on a very extensive assessment that's looking into all the details of what forces drive the emission scenarios of the future. Let's say there was a regime change in China, and the new regime was very committed in ways that the current regime isn't to green energy. What could they do differently? If there was big political changes in the United States, if price of oil fell to this amount, if the price of oil climbed to this amount, what could we do? What are realistic possible outcomes? And so for actual climate change simulation purposes, 4 different narrative storylines, storyline is the vocabulary word here, were developed that consist to describe consistently the relationship between the forces that are driving emissions and how those forces would change over time. Each storyline represents different demographic, social, economic, technological, and environmental sustainability type developments. We're going to kind of come up with 4 different stories here as to how the next 100 years could play out. Now, within there, we might come up with some scenarios that are a little bit different or a little bit more optimistic or a little bit more pessimistic, but overall, we're going to have 4 different storylines that have been developed by these interdisciplinary teams to describe ways that the future could play out. The scenarios cover a wide range of the main demographic, economic, technological driving forces that change the amount of greenhouse gases that are emitted, and they are representative of what's going on in the literature. All of this is based, they aren't just playing Risk here, okay, or some board game or something like that. They're based on actual research. What's a realistic amount of coal that could still be in the crust of the Earth that is economically feasible to recover? What are realistic technologies that could come out that would make it more cost effective to extract methane ice from the seafloor? Okay, if that becomes a cost effective technology, we're going to extract methane ice. Then what? All right, well, we need to know those kinds of things. What are some viable scenarios? The right word that we're using is storylines. Then we'll establish scenarios within. But before we do that, let's actually answer a couple quick questions here. Question 1. We now have several different storylines about how A, the greenhouse gases in the atmosphere will absorb and emit long-wave radiation. B, how climate scientists will interpret the output of their numerical models. C, how carbon dioxide emissions will change over the next century. Or D, how the pre-industrial climate worked. All right, take a look at those 4 options and make a choice and get a little feedback before you move on to question 2 for the lecture.